Today we're going to present Universal Entropy Part 2, in which we recreate for ourselves some of the major results of John von Neumann, who was able to extend in the 1930s the statistical mechanical definition of entropy into a probabilistic theory applicable to quantum mechanical systems. And ideologically, it's really a generalization of the work that Claude Shannon did, although Claude Shannon actually did it later. Von Neumann was very, very precocious, and kind of you think, you know, anyway, it doesn't make sense that it's in reverse like that, but that's the way it rolled out in history. So, as a tutorials to kind of warm up, if you're really stale on the mathematics of the natural logarithm of x and that it equals the integral of 1 over x dx, that sort of thing, you might want to watch this first video here where I derive that in a very, very intuitive and satisfying way, and easy. And also in the second link, I derive the geometrical meaning of the number e. I actually derive the number itself, which is just shy of 3. It's 2.7218218, and then it goes in seemingly random on from there. So I derive the actual number, and then I show geometrically what j means and what it means when you do e to the j, and put an angle in there, what that means. And so if you watch those videos, you would be it would be helpful, and you'd be more comfortable with a lot of what's coming next. So in the green there, I have what we covered in part 1 of this presentation, which I've already done, in which I talk about the earlier history and preparing the way for this. So if you haven't watched part 1, you might want to do that first. And in part 2, I'll just talk about what the first bullet, because I'm going to go through in the interest of saving time for you, I'm going to go through each of these bullets just before we do it in real time in the video. So right now, I just talked about the first bullet. We're going to consider quantum mechanical systems and how to generate the quantum probability tensor from the Bra and Ket notation. Now, I was first exposed to this notation about 25 years ago when I read this book by Paul Dirac. And I think he was somewhat tongue-in-cheek in using the bracket, bracket notation, but it's a good mnemonic, and people like it, so it's in common use, and I thought we should go through it and explain it a little bit. So we'll do that. Now I want to give just a little overview of what these quantum amplitude waves are, and we're going to be talking about just electrons to keep things simple, pairs of electrons in our problems that we're going to be doing, solving for entropy. So quantum amplitude waves for electrons have an amplitude and an angle. So the amplitude is this symbol alpha, and the relative phase angle is this symbol theta. And just like real waves, the waves move through space we call Hilbert space, but it's really just a fancy name for an aspect of the space that we actually live in. It's physically real. Real in the sense that it's physical, tangible, and we live in it. In fact, they've recently discovered that in the last 10 years or so, that without quantum entanglement, photosynthesis could not work. The electrons are entangled, and the reactions can be sustained longer and long enough for photosynthesis to actually function. So without quantum entanglement, we wouldn't even be here. There'd be almost no life on Earth. So it's a real thing. The waves move through space called Hilbert space. The spins up and down travel as amplitude waves. So the amplitude wave is the wave has an amplitude, but it doesn't have a real probability yet. And we'll talk about that. The magnitude representing the probabilities of spin up and down are given by the wave multiplied by its conjugate. In other words, the e to the j, you have to put e to the negative j, or alpha, the amplitude, e to the j multiplied by alpha e to the negative j, which means 1 over e to the j, and they cancel out. You just get the amplitude squared, which is the probability for these amplitude waves. And the probability, yeah, the magnitude of the actual probability, which is just the probability. So the waves are complex numbers, alpha, e to the j, theta, and the probability is given by, I show here the alpha j theta times alpha j negative theta, and it cancels out, and you just get alpha squared. Okay, because e to the negative j theta is 1 over, right? So you see that e to the j theta and e to the j theta cancels, and you just get the amplitude squared. All right. So I'm going to now show you some mnemonics to make the Bra and Ket notation very easy to remember. In fact, you won't even have to try. Just keep your eyes open if you can. And I will encode it in your mind in a way that you can't forget. Mnemonics work very well when the images are very dramatic and illogical and kind of silly. The more sillier, the better. And the images have to somehow encapsulate the ideas that you want to remember effortlessly and probably for the rest of your life, whether you like it or not. So I just want to make it so easy. And you'll see this in the next. So I have to say here, quantum amplitude waves have an amplitude phase, blah, blah, blah. A repeat of what I just showed before. And here's the Bra and Ket notation. Notice bracket, it's like a bracket, right? So when you see a bracket, you expect to, a open bracket, closed bracket. So you get with Bra has an open bracket here, see that? And Ket has the closing bracket in it. So there already is sort of a mnemonic. And we're going to show what this means in detail. But Bra is basically a row vector. So I say here Bra, the geometrical meaning of it. And I say Bra is horizontal. Okay, like real bras are actually horizontal. It'd be funny if women had their anatomy arranged vertically, but they don't. So the bras are horizontal, which turns out to be important because a row vector is horizontal. Okay, and I have this bra. I chose this one particularly because it has flowers all through it, so it's flowery. And the Bra notation has little flowers in it. See. And that represents conjugation. Because when like I said, I read it 25 years ago, and I always had to wonder which one's the horizontal one, and which one has the conjugation. Is that Bra or is it Ket? These things. But now you know the horizontal one is Bra because you got this stupid image in your mind, and you know it has that Bra had lots of flowers in it, so you know the Bra has the conjugation, right? Where you just take e to the j theta and make to the negative j theta. That's the conjugate. And you'll see we'll use that. And the Bra is horizontal. So you probably won't forget that. Now Ket. It's like, did you let the cat in? Did you feed the cat? Okay, so I have a cat. It's like this cat. See this cat hanging on a branch? And the cat is vertical, just like the cat, right? So vertical means it's going to be a column vector. And no flowers. You see any flowers on that cat? No. and so it's not conjugated. Okay, so ket is the one that's got no, it's not conjugated, and it's a column vector. All right. So, and here I have wrote that it's a column vector, vertical. And then let's put the two together, and so we see them both together, the bra and the ket. Now see here, you can take the bra, which is a row vector, and you can multiply it by a ket. Using, I made fun of this when I did the general relativity presentations, how mathematicians love to almost worship this row times column and add, right? Because if they don't, the whole system of modeling that they built is built around for matrices, linear algebra. It's based around the convention that you multiply by row by column and add, right? So we're going to be doing that with these bra times ket, which you'll see. So here we have the row vector bra and the column vector. It doesn't show up when you write it because Dirac has the bracket at the end, but it means a column vector. So I like to, as soon as possible, get that ket into the column vector form. And yeah, I don't like to use notation where one symbolic interpretation, and they make everything concise, and you have to remember, or you have to learn it in the first place, which is worse. But the Bra and Ket notation is not so bad that way. Okay, so now here I show it, like I said. Bra is a row vector, and I show it. And ket is a column vector. So this ket thing, u1, u2, okay? So now, there's the notation of the ket vector, and there's the notation of vector algebra. And I want to cover those together. And then I want to come up with some of my own stuff. Like, what I prefer is that we stick as much as possible to what we learned very early in life. That was addition, subtraction, multiplication, and division. So some of these things, like for example, when you do the probability tensor, it's just a multiplication. I mean, and they call it things like outer product and all that. It's kind of it's just a little bit more abstract than I think it needs to be. So I'm going to show you that, some of the simpler ways of looking at it as well. So let's look. The inner product, which is a term, is equal to bracket. Okay. Now, if you're not familiar with linear algebra, that inner product is not necessarily the best way to describe something. But anyway, I'm going to show you what the inner product is. You take bra times ket. So here we have the bra. Notice it's horizontal. It's got the flowers. Times the ket, which is a vertical column vector. And you multiply row times column and add. So u1 times u1. And then in the place. Oh, let's talk about now. This freaking thing is a tensor, which makes me tense, and it probably makes you tense. But all it really is a little table where you put the terms in based on their subscripts. So when you multiply u1 times u1, row times column, then you get this term it's u conjugated times u1. You get u1 conjugated times u1. It's got the notation 1, 1, which means row 1, column 1, right? You put that little unit in there. That's how the system works. And then then you do so row times column, right? And add. So you got u1 times u1 and u2 times u2. And where do you put this u2 times u2? Well, it goes in that table under the second column, second row, right there. and the rest are not produced by this operation, Bra Ket. So it's just 0 placeholders. Okay. So the inner product is equal to the trace of the outer product, which we're going to, then it says, well, first of all, trace is the diagonal. And you can see right here from the inner product that we did that they know what the diagonal is. But in the inner product, that is, Bra Ket. Well, the outer product is Ket Bra. You flip around the operation, but you still do row times column and add. So here we get row times column is U1 times U1 star. There it is, U1 times U1 star. And where do you put it? Well, it's got the subscripts 1, 1, so it's first row, first column, right? So it has to go here. And we just stick it in there. It's like good housekeeping, okay? And then you go row 1 times column 2, so it's U1 times U2 conjugated. And so where does that go? Well, U1, 2, which means row 1, column 2. So here we have row 1, column 2, and that goes right here in its little place. And then you do U2 times U1, U2 times U1 conjugated, and its subscripts are 2, 1, so it's row 2, column 1. You put it right in here. And then you do U2 times U2 conjugated, and that's got 2, 2 as the subscript, so you put it in its little place, U2, U2 with the conjugation. So that they call the outer product, and it's actually a tensor, which just is an outer product. And I'm going to show below that it's just a multiplication, covering all the degrees of freedom. And so it's the probability tensor they call. We're going to use the symbol P for this, big P, and for probability. And I'm going to show you, and what it does is it represents the probabilities for each of these components. And remember I said that the inner product is the trace of the outer product. Well, this is the outer product, what they call the outer product. And the trace is just the diagonal. And you can see that the inner product truly is the diagonal elements of it. And so it holds up so far. Now another way to do the probability tensor is multiply. So I like that. I want to think that way because it's quite obvious. Now a lot of mathematics and algebra in particular, algebra means that's one on one side and in the other in Arabic. And in the Middle Eastern countries, Arabic and Hebrew, for example, they read from right to left, right? And so they multiply from right to left. And it's kind of interesting because we're in the Western world, we read from left to right. And we should probably multiply from left to right. But since we got the algebra from the Arabic countries, we actually multiply from right to left, just like the Arabs read from right to left. And so I don't necessarily think that's the best thing for us. So I'm going to multiply from left to right. So let's do that. So U1 times U1 star gives us, it's the first term, and we put that in there. See, I'm building the same matrix. Then we do U1 times U2 star, and you put it in its right place. Then you do U2 times U1 star, and put it in the 2, 1 place right here. And then you do U2 times U2 star, and you put it in its place. So this business about outer product and tensor and all these terms that are so highbrow, at least I find that, It's just a multiplication. And we've known how to do multiplications from a very, very early age. So some of these things which seem so complicated are actually completely rudimentary. And once you get into it and you just look at what it really is, like I just did. So, oh, here's a little reminder, because remember, you probably haven't forgotten yet, but if I just remind you now, it'll help, that the bra is a horizontal, as you go, the bra is horizontal vector, and it's conjugated. It's got the little flowers, right? And the ket is a vertical column, which is a column vector, just like this cat. And there ain't no flowers around on this cat. So there, hopefully it's in your mind now, and you probably won't be able to get it out of your mind for the rest of your life, which might not be such a bad thing. So let's see now. Yeah, consider it probably. Yeah, we did that. Now we're going to use these probabilities to calculate the von Neumann probabilities for several example quantum systems. Wow, that's it sounds kind of exciting, and let's do it. I think it is exciting. So just looking at this, Bra Ket, we know it's going to produce the diagonal, yeah, which I show you here. What it is, it's Bra with the horizontal times Ket, the vertical, and we get this after the multiplication. We've already done that. And it's the bracket is bracket. Paul Dirac's notation is equal to the trace of p, and then I show here the trace here. Yeah, it's the diagonal, all right. Notice these terms here, and this term, second term, second term. So it produces what they call the trace, because the trace just means, it's another word for diagonal. Now, why they don't call it diagonal and leave it at that, I don't know. Because trace, there's terminology. So now, and then I do Ket Bra here. We're talking about Ket Bra again, which you flip the order and do row times column carefully, and you get the probability density multiplication, or they call it tensor, as you see here. We've already done that. And then I talk about how the multiplication from left to right gives you the probability tensor. It's just a multiplication of the, as I showed earlier, the let's look at that again. It's the on YouTube. It's the vector, row vector. On the top is the bra, and on the bottom is the unconjugated bra vector. So that's how another way to do this thing. Let's go down. Okay. Done that. So let's now solve the eigenvalues which encode for the probabilities within the probability tensor. And we're going to do this in a general sense, which is where the amplitudes alpha and beta can be basically anything undefined. So we're going to do it first with just the symbols and work it out. And then we're going to do some examples where we have the actual numbers for alpha and beta, and work and see if we get the same thing. So I want to read this part because the information is very precise, and I want to say it exactly correctly. So in order to be able to use a quantum approach for entropy, analogous to what we derived with Shannon's entropy, remember in presentation number 1, that the entropy is equal to the sum over all of the contributors from I equals 1 to n of the probability sub I log 1 over the probability sub I. So we need to be able to extract from the probability tensor, which applies to quantum mechanics and von Neumann solution. We need to start with be able to start with the probability tensor now, and have one or more solutions that represent discrete probabilities, analogous to the Shannon's probabilities, which can perform in the same manner as P sub I used in Shannon's. Okay, so now we get to the point where we're going to talk about what we want. And my approach to mathematics, since I'm more of an engineering designer personality, and where modeling physical reality is very important, and to a large extent other scientists, physicists, especially experimental physicists, and need to have models of reality in order to be able to produce optimizations within systems and equipment and things like that. So we're going to do the same thing, and the specification for what we're looking for is we want to take this probability density tensor here, and we want to be able to put it in a form where we have solutions lambda sub I multiplied by the identity matrix. Okay, so in that form, we're saying, what we're basically saying is this probability tensor is in some fashion equivalent to this lambda as individual probabilities with the solutions times the identity tensor, just to put the lambda into in this case a 2x2 matrix format. So and where lambda represents solutions, right? So then operating on this, which is our specification, but not changing it, we subtract the resulting, when you multiply this, lambdas times the identity matrix from both sides of this expression here to arrive at the following equivalent statement, which is this. You get what we had at the beginning. And remember, x1 times x conjugate 1, those cancel out, the conjugates cancel. And so you just end up with alpha squared and beta squared, beta or beta squared, depending. So and then we subtract this thing over here, which is the multiplication of lambda times the identity matrix. Okay, so you get the key here when you've done all this, and you look at it, you see that you've just subtracted lambda sub I from the diagonal or trace elements in this matrix here. So what you get is lambda squared minus alpha, and alpha beta, and beta alpha, and beta squared minus lambda. And then, because we subtracted it from both sides, is equal to 0. All right. The solution to expressions of this form is found by setting the determinant of the matrix to 0 and solving for lambda sub I. Now, this is a very standard practice in basic algebra. So we're going to do it. And remember, for a 2x2 matrix like this, the determinant is you take this first term here, term 1, 1, and multiply it by this term, which is, what is that, 2, 2, and then subtract this term 1, 2, which is alpha beta, and multiply with the multiplication here. So I'm going to do the multiplication first, then subtract. So subtract alpha beta times beta alpha, and then do the subtraction. Okay, so that's how you get and set it to equal to 0. That's how you get the solution to this expression with involving lambdas. So we do that, and I really believe in spoon feeding. Like, we eat with spoons all the time, so there's nothing wrong with that. So just to help make it clear, I'm just showing the steps of the multiplication here. It's, this times this equals that, and then this times this. Well, in this case, yeah, this alpha sub I sub the beta squared is equal to alpha sub I beta squared. I mean, no surprise there. And then alpha sub I times alpha sub I is equal to alpha sub I, and they're both negative, but and so they turn into a positive, etc. So I multiplied it all out and showed you how. And we end up here with equals negative lambda sub I times alpha squared plus beta squared. Now, we haven't specified what alpha squared plus beta squared is, but we know for probability in general, if you sum all of the probabilities, and remember in quantum mechanics, the amplitude squared is equal to the probability. So there's alpha going on and beta going on, so the total probability is alpha squared plus beta squared. And we know that the total probability is, we know something's going to happen, right? So the total probability is equal to 1. So alpha beta, so it just turns into negative lambda sub I, right? And plus lambda sub I squared, and there we have it right there. And then what you can do it by just observation, but like if you put a 1 in there, it equals 0, so you know that's one solution. And if you put a 0 in there, 0 plus 0 is equal to 0. So, you know, that's a solution. And it turns out those are the two solutions. Now, if you remember, we're getting, there's two solutions, so each of those is a probability, and you want the total probability associated with performing the sum of I equals 1 to n of alpha log 2 of 1 over the probability. It's very funny, this guy's gone up here. I wonder, let's move it down so you can see it. There we go. Little guy's running away from me. So yeah, we put it in the form of Shannon's, but we use the probabilities derived through von Neumann's method. And we get lambda sub I times log 1 over lambda sub I, where lambda sub I is performing the same functions as p sub I in Shannon's theory. Okay, so what this is we have we put then these two solutions. There's only two of them, so it's equal to 0 log 2 to the 0 plus 1 log 2 to the 1, and that's both of these are 0. So we get the total entropy in the general sense is equal to 0. So that's a really important result. And this is for the entangled situation for two qubits, for example. Let's go on here. So let's examine one of the simplest cases, two qubits whose spin states are entangled, okay? And where the probability, unlike the general sense, remember I said I'm going to do it in the general sense, then we're going to do a few examples, give us more practice, and also to see with real, some people find it easier to work with real numbers. So here we're doing it where they're equal, and this a squared plus b squared equals 1, so each one is going to be 1 over the square root of 2, right? When they're equal. Yeah, when you do this, you square 1 over square root of 2, you get 1 half, and then you do another one because there's two of them. 1 half plus 1 half equals 1, which is a requirement. The total probability, which is usually along the diagonal of the probability tensor, is equal to 1. So there we have it. Okay. So, I'm now putting the state, one of the states of the qubit into the terminology alpha x1. Have x1 is equal to e to the I theta. So it's a complex. It's part of a wave. So you have to represent it because the phase changes, right? And that's an angular relationship. And I explained that in the tutorial that in the beginning of part 1, I give you the link for that. All about what E sub I theta means and derived, showing what it means geometrically. So you might want to check up on that if you still are not familiar with that. And then likewise, beta x2 is equal to beta e to the j theta, where number 2, just to keep track of them. And then I show what's you already know, really, if you know this stuff, that the complex conjugate of alpha x1, which is shown by that star on the top, is equal to, that it's a conjugate, is equal to alpha 1 e to the negative. You just change the angle from being a positive 1 to a negative 1. And beta alpha 2 conjugate is equal to beta e to the, or beta x2 conjugated is beta e to the negative theta 2, okay? So, and then to calculate the probability tensor, I've shown you this before, and I'm going to use one of the 2 methods I showed here, which is a simple multiplication. You take remember Bra and Ket, you take a bra, but without conjugation, and you multiply it by a bra with conjugation, and you actually, it's one way to get the probability tensor. And then I show how this goes to here, and that goes to there, through the multiplication process. When you multiply alpha x1 times alpha x1, and you get with conjugation, so that's the term 1, 1, right? And then you have beta x, alpha x1 rather, right here. Alpha x1 times beta x2 conjugated, and then that goes over to term 1, 2, and you get that. So you do the same thing here, and you would multiplying that and then multiplying that next, and you get these 2 terms. So that's how I was showing you that before. I'm giving this as kind of a little review. And the e to the I theta is what it is, and e to the negative I theta is 1 over e to the I theta. So they cancel, and you just get alpha squared as being that term. And likewise here, these 2 ones on term 2, 2, the complex conjugates cancel, and you just get beta squared. And the conjugates cancel here, and you just get beta alpha, and the complex conjugates cancel there, and you get alpha beta, okay? Now we know, we've already talked about it before, that alpha and beta are equal to 1 over square root of 2, so you multiply them together, you get a half, 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 half. So we have solved the probability tensor in this case in terms of real numbers, okay? And you can basically look at this and read the solutions off. I mean, we're going to show other ways where you solve the eigenvalues, but this one, it's like a half times x1 is equal to lambda x1, so you know the lambda is equal to half, right? And half x beta beta x2 is equal to lambda x2. So but let's actually work it out. I'm just pointing out you can solve some of these with just inspection. But let's go to the next chart. I think we'll work it out here. Yeah, so there we go. The solutions for lambda express ways to replace the tensor P with single probabilities analogous to the probabilities used to produce Shannon's entropy. So we've been through that, and I show you Shannon's entropy again. Okay, let's solve for lambda in the usual way we solve for eigenvectors using the determinant of the probability tensor minus lambda sub I, okay, and set that to equal to 0. So we did that earlier in the general case, remember, and I promised I was going to do it with real numbers. So here we're doing that. So the probability tensor minus lambda sub I is equal to this. Remember I talked about how you just take, it ends up being you take lambda sub I away from the diagonal, the backward leaning diagonal terms, okay? So, and then you set the determinant of this, because this is the same, to equal to 0. There's 0. And it works out to 1/2 minus lambda squared. See, this way, right? Multiply this way. And then you multiply the other way on the forward leading diagonal. Multiply those. This is how you do a determinant with 2 by 2 matrix. And then subtract. So we do that. And this is 1/2 by 1/2. So you subtract 1/4. So you've done that job. And multiplying these two together is 1/2 minus lambda squared. You got that written down, right? And then you go through the arithmetic, and what you get is that there's two solutions. One is lambda sub 0, and try it out. You put 0 squared is 0, minus 0 is equal to 0. Bingo, it's a solution. And then you get lambda equals 1. Okay, let's try that one out. 1 squared is 1, minus 1 is equal to 0. Yes. So we did the debt approach, and we solved the characteristic equation, and we got these two solutions. And you have to add the two solutions together. Don't forget that part. And so what we get is that, again, the same result. Remember, we derived this for the general case where lambda and beta are not, the amplitudes are not necessarily equal, and then we got that the entropy was 0 for that situation. And then we did it for the case where they were equal, and they're equal, both amplitudes are equal to 1/2, right? We got the same result, that the total entropy is equal to 0. This is a von Neumann with double N. Of course, now I can't. Von Neumann entropy. I'm going to take out something to get it back. Oh man. I'm just going to call it the Neumann. I want to get it all in one row. The Neumann entropy. Great. Great, so you can see it all. All right, so let's go see what the next step is. Okay. Then we're going to compare the system entropy after the spin states lose coherence, and find out what happens to the entropy, which right now is, in the general case and in that specific case, is equal to 0. Okay, what happens when you destroy the entanglement? And then we're going to find out what entanglement does. When we think about it, we'll know what entanglement does to the entropy. Does it make the entropy go up? Does it make it go down? Does it keep it the same? And by how much? Okay. So let's look. Let's look to do that. And we're here. We'll go to the next one. All right. So here we say, I want to get some kind of arrow. So let's copy this. And let's use it. Okay. Solution. Oh, I don't use that. Solutions for the general case with mixed states are lambda equals 0 and lambda equals 1. And you know what, the result of that. And the von Neumann entropy was equal to 0 for that, for the general case and in the specific case, which is no surprise. So we come up, this is a result then. After the measurement of one spin state, the superposition of states is destroyed. That's an experimental fact. Hence the cross terms in the density matrix go to 0. So this is what I'm talking about, the cross terms, these ones and these ones. And they're the mixed states where you have the beta amplitude and the alpha amplitude multiplying. And we want to just have the pure states where it's purely state 1 or state 2, but not both, okay? Or at least not correlated by having entanglement, okay? So we're going to operate on that probability tensor, this one, with the subtraction of the lambdas in order to put it in a form where we can get the solutions lambda, okay? And applying the det p equals 0, we multiply across the backward leaning diagonal, these two terms, and then across the forward leaning diagonal. And the backward leading diagonal of these is this this times this. So it's funny when you say something. Okay, and that's whoops. This here should be a multiplication. Great, I got it. Yeah, so so when you multiply those out, right here, half times a half is a quarter, half times minus lambda. This is just minus a half minus lambda, and another half minus lambda here. Give you just minus lambda, and then lambda times lambda is lambda squared. So that's the characteristic equation for this. And the eigenvalues, the solutions, are lambda 1 is a half and lambda 2 is a half. Now, one of the things you can trip up on this is you get the solution lambda equals a half, and the other is lambda equals, you think you have one solution. Well, actually, you have two probabilities that just happen to be equal to each other, okay? So you have to add the two solutions. And you get that the solution then becomes a sum of lambda sub I log 1 over lambda sub I from I equals 1 to 2, right? And that is equal to 1/2 log times log 2 of 2, to log base 2 of 2, plus 1/2 log base of 2 of 2, and that's equal to half of 1 plus a half of 1, which is equal to 1. Half plus a half is equal to 1. There it is. Okay. So what we just derived was that the von Neumann entropy of both states of an entangled electron pair with spin superposition of states is equal to 0. The entropy is equal to 0, which means you have all the information. The entropy is the information you don't have, the minimal amount, knowing all the things that you know at the moment, that the logarithm of 1 over that probability. We know that the entropy is equal to 0, so which means that if you perform an experiment where you measure both states at once in an entangled situation, you don't learn anything because you already know everything you can know. When the state reestablishes itself and you still don't know what the respective states are or anything more. So the entropy is equal to 0. We eliminated the cross terms, destroying entanglement. The entropy went up to from 0 to 1, right? We thereby discovered that entanglement reduces the entropy of a system because you took the entanglement away and the entropy went up from 0 to 1. If you put the entanglement back, the entropy will go from 1 to 0. It lowers the entropy of the system. So you might wonder, why would entanglement lower the entropy, right? So let's go and have a look at that. We just arrived at the von Neumann entropy for both states of an entangled electron pair with spin superposition of states is equal to 0. Okay, this means that we learn nothing about the system by a single measurement of both states at once. Okay, we've been through that. Let's use an arrow. We eliminated the cross terms by destroying entanglement. The entropy went up from 0 to 1. We thereby discovered that entanglement reduces the entropy of the system. Great. Nice little review. Why? Why does the entropy lower the entropy? Okay. Why does the entanglement lower the entropy? Okay. So I'm saying here, remember that our Shannon work showed that entropy goes up as the number of splits within the system goes up. Now I'm referring to Shannon by analogy, okay? So when the number of symbols is 32, the system splits into 32 states, and the entropy per symbol is log 2 to the 32, and that's equal to 5, okay? So you can see there's a relationship between entropy and the number of ways that you divide the system. Okay, and I'm doing an abstract way of thinking about division. Remember, we had for the Shannon entropy, and in presentation one, we had this tree where splitting into all the possibilities. Okay, if the number of splits goes up to 48, 48 symbols, then the entropy is log 2 to the 48, which is 5.585. So you can see a relationship between this division of the system or splitting of the system and entropy. More separate components in the system, generally the higher the entropy. So when we entangle two electrons, the two independent states become unified into one entanglement state, which reduces the number of splits. Another way of looking at it is reduces the number of degrees of freedom within the system, thus lowering the entropy. So it's actually it's intuitively satisfying that when you combine the states into sort of one distributed state, whereas before there are two separate ones, that you're reducing the number of possibilities in some manner and the degrees of freedom. And when you think that way, you would expect entropy to go down when you do the process of entanglement under these sorts of conditions. All right, so here's a little bit of a summary. I want to talk about, people wonder, what is entropy? And you get all sorts of answers, right? So I want to just, I want to try to, I did a universal theory here where I showed that the major historical versions of entropy all have a common substrate, in this case symbolic substrate, but nonetheless the same thing. So I'll review here. Rudolf Clausius / Gibbs, because I took the classical thermodynamic method and in this expression to put it in probabilities, where it was Gibbs who did that with statistical mechanics, okay? But it's there, both of their contributions clearly. And then these are just constants of conversion to make sure the units are correct. So the entropy is equal to the amount times the, what is that? The Boltzmann's constant times the natural logarithm of 1 over the probability, okay? So that's what we learned there. And the Shannon entropy is the sum of the contribution of the various terms, the logarithm again of 1 over the probability times the probability, because each term has its contribution that's proportional to the frequency of its occurrence, right? Which is another way of saying the probability, right? So you have to multiply by that. Add them all up. Then the Shannon's conditional entropy is where it's basically this, but where this p sub I is equal to the branch probability, and I even say it there. Same expression. This was substituting p sub I with p of the entire branch. You got to multiply it through for each branch of conditional probabilities. Okay, so that's that. And then the von Neumann entropy is k some constant of proportionality times negative sum 1 to n of alpha sub I, of the lambda sub I log lambda sub I, where lambda sub I is clearly taking the role of the Shannon probabilities. And if it was conditional probabilities, well, yeah, you'd have to do the same branch probability thing, I think. But ultimately, so we get this expression here. So I notice all forms of entropy use the same kernel definition of entropy, namely log 1 over p, or equivalently log p sub I, okay? Equivalently. And in this expression here, notice it is log lambda sub I, which stands for log p sub I, right? So that's why I have a negative in front of it. It's from here. We can thus see that entropy is universally a measure of the minimum uncertainty, because this represents the uncertainty, the probability represents the uncertainty given all the things you can find out about the system. So there's not anything more that you could extract out of the system. So the uncertainty that remains is the minimum uncertainty. And that's the uncertainty we are referring to when we talk about entropy. Okay. The exact form taken by the entropy depends on the system you are analyzing and what you intend to use the results for. So some people, I've heard physicists say, people don't know we don't really know what entropy is. And I think that's true if you think of, we don't really know of one definition that totally applies to all forms of entropy. Because it really depends on, I'll just say here when I said it well here. The exact form taken by entropy depends on the system you are analyzing and on what you intend to use the result for. So we shouldn't expect to have one definition of entropy apply universally for all the different systems. But the same basic kernel here applies, right? So for example, in the case of a binary coding, you're interested in the number of bits required per binary symbol. So you use entropy is equal to log 2 to the 1 over the probability, okay? So that answer is, and then it's expressed in bits per symbol. For thermodynamic systems, classical thermodynamic systems with going as far as Gibbs, we are interested in the total area under the continuous curve of improbability, calling 1 over p the improbability, because the bigger the improbability, the lower the lower the probability. Let me think now. The improbability goes up as the probability goes down. So if you 1 over the probability p, as p gets smaller, 1 over p gets bigger. So that's the improbability. Or another word is uncertainty. So we use for thermodynamic systems 1 over p, and that form takes, when you work out the entropy, the constant of proportionality here, times ln 1 over p. With ln here, log 2 there, lambda over in von Neumann entropy. The core of the idea is probability. This one logarithm of 1 over p, or negative logarithm 1 over p, negative logarithm of p and logarithm of 1 over p, okay? Same idea. So behind this mirage of all these nuances in the actual expressions for entropy, the same idea. It's just because you're looking at different systems, different units. Like, for example, a binary information encoded system is so dramatically different than a physically encoded system where you have atoms in some kind of vapor and pistons, just to provide a stark example of how broadly applicable the basic core idea of entropy is, and how dependent it is on the specifics of the physical implementation, for the exact form it should take. So I think we do know what entropy is, but it just is, the exact definition is system dependent. So here I want to give a view of where we've been and how we've done. The green ones up top are just to give you an idea of what we covered in the previous part 1 of universal entropy, which you can look up. And let's look here with the black portion is what we went through today. You've probably seen this before in the presentation. We said we're going to consider quantum systems and how to generate the probability tensor from the Bra and Ket notation. And we did that. Remember, we went through the notation of Dirac, and I gave you those mnemonic images, which you'll never forget. Bra and Ket, what they mean, and how to use the Bra and the Ket to calculate the probability density tensor. We've done all that actually a few times. So yes, then use these probabilities to calculate the von Neumann probabilities for several example quantum systems. We did that. We did that with entropy, with entanglement, and without entanglement, working out the entropies. Solve the eigenvalues which encode for the probabilities within the probability tensor. We did 2 or 3 examples of that, one in the general case, one in the specific case, and then the other ones with and without entanglement. Which brings up the next one. As an example, compare the entropy of 2 entangled electrons in a state of superposition of spins, then compare the system entropy after the spin states lose coherence. Find what happens to the entropy of the system once its entanglement is lost. Once entanglement is lost, the entropy goes from 1 to 0 in the examples that we did. And then provide an example of why we should expect this change of entropy to occur, which the change is that entropy brings this change of, why we expect the change in entropy, which is going from 1 when you do have entanglement, down to 0 when you do not have entanglement. Oh, wait a sec. The 0 is for the system with entanglement. Yes, so entanglement lowers the entropy from 1 without entanglement to 0 with entanglement in the examples that we showed. And the explanation, remember, it was because if you take an entangled system, one depends on the other, reduces the degrees of freedom, so the entropy goes down. If you have you separate those systems into 2 separate components, the degrees of freedom go up, the number of ways of conceptually splitting the system is greater, so the more information, and the entropy goes up when you remove the entanglement. So entanglement reduces entropy, and you should expect it to do just that for the reasons I described. We did that. Okay, so let me just say, I really, it was a privilege today to be able to present this to you, and I really enjoyed it so much, and I want to thank you for watching, and have a good day, and I hope you got something from this, that you liked it. Bye.